Hi, my name is Bernard Brault. I'm with OTN Systems. This is part 2 of a IEEE 1588 transparent clocking demo. So I'm inviting you to watch part 1, or the first video I did on transparent clocking. Transparent clocking is part of the power profile of IEEE 1588. So 1588 is all about synchronizing clocks between grandmaster clocks or high precision clocks that could be in a critical location like your control center, backup control center, or other critical location where you'd spend or invest a great deal of money on a high precision clock. And then you'd want to synchronize boundary clocks, maybe inside your critical substation, or maybe eventually in all of your substation. And ultimately, the boundary clock acts as a master for ordinary clocks distributed inside your substation and every device that needs precision timing. So 1588 is the protocol that's used between master and slave, and it's runs over Ethernet or runs over IP. And what you have in between is you have network elements that support, for example, transparent clocking like the Extran. And I'll show you the benefit of doing transparent clocking. The purpose of this video is not to explain how it works, but to show you, what it does. So in the first video, what I had is a 6-node Extran network, and I had a master clock at one end and a slave clock at the other end. And I established a 1588 service over Ethernet, and showed you the benefit of enabling transparent clocking. It allowed the slave to be far more precise. We achieved something like plus minus 20-30 nanosecond, if I remember, and while we had like a disturbance traffic in between. But in a real live network, you would have something much bigger than this. So what I want to show you here is something that's a bit more realistic. So this is like either a section of a network that's a couple hundred nodes large. Again, you'd have your master or grandmaster clocks and your control center or strategic location, and the boundary or slave clocks would not be like 1 or 2 hops away, but it'd be like something like 20 or 30 hops away from the grandmaster. And the key question is, how can you achieve high precision in the slave clock, considering that you have so many network elements? And as you increase the number of elements, you're increasing also the jitterness of the network, and because of the packet delay variation adds up across all the hops. So in the demo I want to do, I'm going to have transparent clocking over 41 hops. So one end of the network will have a master clock, and the master clock is going to go over 41 hops, and at the far end you'll have the slave clock. And what we're going to show you is what happens when you enable transparent clocking. It allows for an application like this where the slave can run with very, very high precision. Actually, what's interesting is that when I disable transparent clocking across a network like this, I could not get the slave clock to actually synchronize to the master. There was just too much packet delay variation, especially when you start adding disturbance traffic across the entire network except for the two ends. What's also interesting is that a chain has the strength of the weakest link, right? So transparent clocking works, but it has to be enabled across all the ports and across all the devices involved in the 1588 service. So that means in this case across the entire network of 41 hops. And what I'm going to show you is by adding one network element. Alright, so this is an external network element. It happens to be a carrier grade switch, and that without transparent clocking, and it'll provide the equivalent of a E-line or VPLS or MPLS service between these two Extrans right there, but it's going to go across a hop that doesn't have transparent clocking, and I'm going to show you the effect of breaking that chain. So of course, if we enable transparent clocking in this network element, it wouldn't have the issue. The problem is not that it's not an Extran. The problem is that you're breaking the transparent clocking chain. So I don't have the benefit of having 41 hops in my lab environment. So what I'm going to do is a bit of a trick. So I have these 6 nodes again, and what I'll do is I'll establish 7 VLANs across the 6 nodes, and I will loop back here, physically loop back these Ethernet ports at each end. And this is like the same, you know, Extran. So it's as 1, 2, 3, 4, 5, 6, 7 VLANs, and I'm looping back the VLANs back and forth so that, you know, effectively what I end up having is transparent clocking or 1588 traffic flowing across, going back and forth 7 times across this network. And I will inject disturbance traffic in the middle right there. Eventually I'll show you that I will break the connection, the fiber optic connection between these 2 Extran, and introduce a carrier grade product, a switch that is a high-speed switch with very little latency, but you know, it doesn't have transparent clocking inside of it. All right, so that's the that's going to be the demo. So let's take a look at the actual setup. So what you see now is a TX-Care network management screen of the Extran. Here's the 6 nodes, and let me show you the 1588. So I'm going to have a master clock that's going to be connected to node 31 there. It will flow across the entire 6 nodes and terminate at the other end there. But before I terminate, I will loop back 7 VLANs. So it's going to flow back and forth and back and forth and back and forth 7 times, and finally be terminated at the far end down there. So in node 31, I have a tester that's a NetProbe 2000 that supports the 1588 master and a 1588 slave, and this is the GUI for the first NetProbe connected here, and this down there is the GUI for the NetProbe connected to node number 4. Over and above that, I will have disturbance traffic flowing between node 5 and 6, and that disturbance traffic will affect all 7 VLANs that are crossing here. To have a better view of this, if I select this particular link down here, this fiber optic link between the 2, so you could see if I zoom in here, the 1588 has the 7 VLANs that I'm talking to you about. So injecting the generator comes in here, goes on the other side, and then physically externally is looped back and forth and just flows back and forth, back and forth, back and forth until it reaches the last port, and then it comes out. And then there's disturbance traffic that's going to be turned on and off between these 2 sites right there. All right, so let's first thing I want to do is show you the traffic flow of both the 1588 service between the master and the slave, and I'll show you the disturbance traffic, and I can do this on the performance tab. So the top chart there is the traffic for the 1588, which is a synchronization traffic, and the bottom is the Ethernet disturbance traffic. Before I turn on the clock, let me just show you more or less what the latency and the packet delay variation is on this link. So what I'm going to do is turn on a traffic generator instead of the master clock on this one, and I'm going to do a loop back at the far end. So one of the NetProbe 2000 is going to be set as a loop back. So I'm going to start the loop back at layer 2 and look at the traffic here, and I will inject 30 kilobits per second, and that's more or less the flow rate of the transparent clocking, and we're going to take a look at latency. So I turn this on, and we see receive transmit, so we are receiving the packets from the far end, and what's interesting is to look at the latency and the packet delay variation. So we see here that we have a minimum of 625 microsecond latency across these 41 hops and a maximum of 642. And if I turned on the, let me bring the disturbance traffic generator. If I turn on the traffic generator there, and you'll see that the disturbance traffic is going to start growing up here. So that's the bottom disturbance traffic is shown down there, and again we have 622 versus, now you look at that, you know, quite quite a bit of difference between the two. So you can see here that, as you know, this is creating a fairly substantial packet delay variation, you know, in large number of microseconds between a minimum of 622 and 1134. All right, so let me stop this flow, and let's go back and stop the traffic generator. And this time what we're going to do is set this port here as, sorry, this tester as a master clock, and this other tester here as a slave clock. So I'm going to start the master, and you can see traffic from the master, and then the slave, I'll start the slave, and the slave will start responding back. So let's take a look at the messages. Yeah, so they're transmitting, receiving messages, and let's just go and take a look at the results on the slave and see how it's synchronizing. So as you can see right now, it's this is the deviation from the master clock, and you see that it's gradually moving towards 0. I'm going to give it a chance to settle and let the graph flow to the right so that the scale can change. So let me just pause this video for a moment, and I'll be right back once this is like in a different scale. Okay, we're back, and as you can see here, this is when I turned on the service and it started synchronizing. And as you see, across 41 hops with transparent clocking enabled, we have a slave that's running plus minus more or less 50 nanoseconds. So that's 0.05 microsecond. That's quite accurate, even going across so many hops. And I can turn on the disturbance traffic, and you'll see the disturbance traffic going on, and turn it back off and turn it back on, and as you can see here, it does not affect the quality of this clock. So what I'm going to do next now is I'm going to go to insert the carrier grade E-line or switch in the middle of the network. So let me show you this. And so I'm going to break this link and connect it to an external switch. So just 1 second, and you will see that's going to go in alarm, and we'll connect it across external switch. And if I go, you see it's gone red, and it's going to come, the service should be coming back. So of course, doing this, we've lost completely both types of traffic. As you can see now, the disturbance traffic is coming back, and so is the transparent clocking. So let me turn off the disturbance for a second. So it's turned off, and again what I'm going to do is let this slave go and stabilize, and we'll be right back. Okay, so now I'm back, and the slave clock has stabilized, and there is no disturbance traffic. But what we did is we put a network element in between the X-Strand that doesn't support transparent clocking. That network element could be, for example, a E-line service, or it could be a VPLS, or something like a private E-line service with some network elements in there that do not have transparent clocking. So without any disturbance traffic, as you can see here, we're still within 200 nanosecond, plus minus 200 so nanosecond, which is not so bad. The problem is, as soon as we introduce disturbance traffic, and I'm just starting the disturbance traffic generator, then all of a sudden, you know, hell breaks loose, and as you can see right now, we're swinging up and down by something like 15,000 nanoseconds. So 20,000, that's 20 microsecond, and we're trying to achieve sub microsecond precision in a slave clock, and we're not going to do this. As you can see right now, it's just going to swing back and forth, swing back and forth. So a chain's got the strength of the weakest link, and transparent clocking is a fantastic tool. A couple of things you need to make sure is that every network element in between supports it. As you can see, it does magic for you when you have it. It really allows you to have a alternative to GPS or satellite clocking that you won't be able to necessarily rely on. But this service needs to be fully tested, and you need to make sure that every single element has 1588 transparent clocking in between. Thank you for watching, and please give us a call. We can explain in detail how this works now that you've seen what it does. Have a good day. Thank you.